This was the moment everything changed for Horizons. The impact landed in 2012 with AMPS, Almary Maroff Polchinski Sully. They pushed the logic. You can't have all three: unitarity, effective field theory outside the horizon, and no drama at the horizon. Drop one. If you refuse to drop unitarity and you trust the outside physics, the horizon can't stay smooth. It becomes a firewall, high-energy quanta right at the boundary, incinerating anything that tries to pass. The equivalence principle takes the hit. Not you'll feel nothing, but you'll feel everything immediately. Get this, the firewall isn't an add-on explosion. It's bookkeeping forced into physics. The entanglement that used to sew the inside and outside into a seamless vacuum has to be cut. Cut the seam, and you expose energy. What looked like empty space turns rough. The quiet doorway becomes a blade. But there was one problem. Nobody can go check. The horizon is a one-way conversation. Even gravitational waves from colossal mergers tell us about the outside ringo, not the microscopic stitchwork at the edge. And critically, there is no direct experimental evidence for or against firewalls. Any tests must be indirect. So the debate went holographic. If gravity in a volume is encoded on a boundary, maybe the information never really disappears inside. It was always on the edge. Add SCFT gave a laboratory. A black hole in the bulk matches a hot quantum system on the boundary that evolves unitarily. That leans toward the page curve. It also hints at something deeper. The interior might be a code, not a place. Meanwhile, theorists tried to save no drama without losing the book. Fuzzballs from string theory replaced the black hole interior with a tangle of strings. No traditional horizon to cross, just structure all the way down. Equals Epper suggests entanglement and wormholes are two faces of one idea. The interior could be connected to the radiation by non-traversable bridges, keeping the horizon calm while information sneaks out in correlations. Soft Hair proposes that subtle, low-energy excitations, charges at the horizon, store details of what fell in, tagging the outgoing radiation with a faint signature. And then came a surprise from the entropy accountants. In 2019, using replica wormholes and quantum extremal surfaces, new calculations reproduced the page curve from semi-classical gravity. Radiation entropy rises, peaks, and falls as if information does come out. That supports unitarity, but it doesn't show you the mechanism in everyday space. It whispers islands, regions that count as part of the radiation's entanglement wedge, even though they lie where we'd call inside. The boundary between in and out blurs in the math. The simplicity of here and there starts to wobble. Microstory, a grad student stares at a plot that dips when it shouldn't. The professor says, "That's the page turn." The student laughs from relief, then pauses. If the curve's right, what does an astronaut feel at the horizon? The room grows quiet. That's where equations run out of comfort. So here's the fork Hawking opened. Keep unitarity and accept that the horizon either isn't smooth or spacetime's bookkeeping is stranger than intuition. Keep no drama, and you're forced to let information die, breaking quantum theory. The glow at the edge isn't the problem, it's the promise. If radiation carries the story back, something fundamental has to give at the limit we called empty. And that limit is where we're headed next. The page curve, when entropy turns around. To see how the glow could keep its promise, we need to track the bookkeeping itself. Entropy isn't a vibe, it's a count. How many microscopic ways the radiation could be, given what we see. Early on, Hawking radiation looks random, so the entropy of that radiation climbs. More quanta, more ways to arrange them. If nothing ties those quanta together, the climb never stops until the black hole is gone. That's Hawking's cliff, a straight line up, then a drop to zero only because there's nothing left to radiate. But that shape hides a crime. It erases the past. Don Page asked a sharper question. What would the entropy do if information isn't destroyed, just scrambled and released? His answer sketched a different arc. Entropy rises at first, as the radiation is genuinely mixed. Then halfway through the evaporation, it hits a peak and starts to fall. Why? because the later radiation carries correlations with the earlier stuff, knitting the whole into a purer state. It isn't that the photons suddenly develop personalities. It's that the joint pattern matters more than any single piece. The curve turns. That turning point is the page time. Stakes right here. The page time draws a line through every story we tell about black holes. Before it, you could still believe the horizon is quiet, the quanta outside are forgetful, and the interior holds secrets. After it, if unitarity is true, the exterior radiation has to start behaving like a codebook. That forces a choice at the horizon we just set up. Keep the seamless vacuum and you block those correlations. Allow the correlations and you tear the seam. The page curve isn't a doodle, it's an ultimatum. Action moved from thought experiments to controlled arenas. In anti-de Sitter space, where gravity plays on a stage with walls, the holographic dictionary says the boundary quantum system evolves unitarily. Translate that into bulk language and a black hole there must obey the page curve. For years, this felt like a promise without a recipe. Then the recipe appeared in an unexpected place, the entropy formula itself. Semi-classical gravity lets you compute entanglement entropy using replica tricks, copying the system n times and gluing them into a neat geometry, then taking a limit. Most of the time, you assume the copies don't talk. Here's where it gets interesting. In 2019, theorists found new saddle points, geometric contributions where the replicas connect through wormhole-like bridges. Add those, and the entropy calculation flips character after a certain time. The minimal quantum extremal surface that anchors the counting jumps from outside the horizon to a surface that wraps around a chunk of what you'd call the interior. That chunk, an island, counts as part of the radiation's entanglement wedge. The math doesn't care that, in ordinary language, it sits behind the horizon. It's included because it lowers the entropy. Impact, immediate and unnerving. With those replica wormholes, the radiation's entropy follows the page curve. It rises, peaks, and falls in exactly the way unitarity demands. No hand-waving about future quantum gravity. The result comes from semi-classical gravity plus quantum extremal surfaces. It says the bookkeeping can be consistent without a visible breakdown of physics outside. But there's a cost. The notion of inside and outside isn't absolute. What counts as part of the radiation depends on what you're asking and when you're asking it. Meanwhile, something else was happening in the background conversation. This page-compatible entropy doesn't tell you how to decode the message. It only guarantees that a message is there, hidden in correlations spread across astronomical numbers of quanta. Computational complexity enters like a quiet bouncer. Even if the radiation contains the story, actually extracting it might take longer than the age of the universe. Some argued that if decoding is practically impossible, maybe the paradox was a mirage. But the page curve doesn't care about our patience. It's about what physics allows, not what laptops can handle. A micro story from that moment. A postdoc prints two curves, Hawking's straight rise and the newly computed page curve. On the board, they cross like two roads that refuse to share the same town. They circle the peak in red. If this is right, someone says, the island is real. Another replies, real where? The room laughs. The line between geometry and information just moved under their feet. This was the moment everything sharpened. If the radiation's entropy turns around, the late quanta are tied to something we used to think was inside. Keep no drama, and you're forced to accept that the interior exists only as a code reconstructed from the outside, state by state. Accept a literal interior as an independent place, and the page curve can't turn without breaking entanglement monogamy. The firewall argument didn't vanish, it changed shape. Either the horizon's vacuum structure fails for an infaller, or the interior for that infaller is nothing more than a story consistent with what the outside knows. In the aftermath, proposals split along that seam. equals Epper fans saw the replica wormholes as hints that entanglement really does lay spacetime, with non-traversable bridges bookkeeping the correlations. Fuzzball advocates said, look, the page curve matches because there's structure at the would-be horizon doing the encoding all along. Island enthusiasts stayed austere. Don't picture the island, just use the rule to get the right entropy. 3 accents, 1 claim, the curve turns. What nobody knew at the time was how that turn would feel to a falling astronaut. The math respects unitarity and keeps the outside calm. Does the seam cut for them? Or does the code conjure a smooth interior for as long as nobody tries to decode the radiation? That's the question waiting at the edge, and it leads straight back to the fire. AMPS, the firewall argument lights the fuse. 3 ingredients sit on the table, and AMPS refuses to sweep any of them away. First, unitarity. The global quantum state that includes the black hole and its radiation stays pure. No lost pages. Second, effective field theory outside the horizon. Far from singularities, ordinary quantum field theory works, and local physics doesn't suddenly bend its own rules. Third, no drama. A freely falling observer crosses the horizon and, for a huge black hole, feels vacuum, nothing violent. The original bargain of relativity. The paradox comes from trying to hold all 3 at once. Start with the late-time photon, the one emitted after the page time. Call it B if unitarity holds. B has to be entangled with the earlier radiation. Call that R, because that's how the total state purifies. Those correlations are the only way the page curve can turn down. But in a smooth vacuum at the horizon, B is also entangled with its interior partner mode. A, the one that fell just behind the horizon when B escaped. That's the local Reindler vacuum, how empty space looks near any horizon. Here's the snag. Quantum entanglement is monogamous. If B is highly entangled with R, it can't also be highly entangled with A. You can't be maximally committed to 2 different partners. AMPS frames it as a choice. Keep the B, an entanglement, and you preserve no drama for the infaller, but then B can't be correlated enough with R to purify the radiation. The page curve refuses to turn. Unitarity breaks, or cut the B, a tie so that B can knit with R that saves unitarity, keeps the page curve honest and respects effective field theory outside. But cutting the tie changes the local state at the horizon. Instead of the entangled vacuum, you get excitations. Energy, a wall of quanta where there should be calm. That's the firewall. Stakes in human terms. The difference between drifting through a doorway and hitting a blast furnace. If the horizon is smooth, astronauts fall through without noticing anything special. If the correlations have to jump from inside to outside, the interior partner mode A isn't there to cancel the vacuum fluctuations. The infaller doesn't feel quiet space. They meet a bath of high-energy modes. The equivalence principle, the bedrock promise that local free fall erases gravity's tug, takes a direct hit at the place we most wanted it to hold. AMPS pushes further with a thought experiment. Imagine a patient, ridiculously advanced observer far away who collects early Hawking radiation R and performs some insane decoding to distill the particular subsystem RB that purifies the late mode B. Yes, it's astronomically hard, but physics doesn't get to hide behind difficulty. In principle, it's allowed. Now they bring RB close and compare it with B as it emerges. If B is entangled with RB, it can't also be entangled with a behind the horizon. The monogamy conflict is operational. Either the decoding works and no drama fails, or no drama survives and we give up unitarity or outside locality. There's no coast to hide on. The action moves to assumptions. Could effective field theory near the horizon subtly fail, even outside, so that decoders can't actually do the distillation without disturbing the black hole? Some argued complexity makes the decoding effectively impossible, protecting the horizon. AMPS counters. Complexity isn't a law of nature, and the paradox doesn't depend on your computer budget. What if the interior isn't independent at all? Proposals like state dependence and mirror operators say it isn't a separate system. It's encoded non-locally in R, then B being entangled with R doesn't violate monogamy, because A and R aren't independent. AMPS replies, "Be careful. If interior operators depend on the global state in a way that can't be made consistent for all observers, you risk contradictions when two people try to compare notes, even in principle." Meanwhile, something else was happening in the background. Fuzzballs sidestepped the horizon entirely by replacing it with structure. No smooth vacuum, no B, a pairing to start with, so no firewall. The fire is spread throughout the microstate. equals EPR offers a different escape hatch. Identify entanglement with wormhole geometry so that B's purification with R is a geometric connection, not a competing bond. AMPS doesn't claim those roots are wrong. It says you can't keep all three assumptions unless you pick one of those radical pictures. The comfortable, classical horizon can't coexist with strict unitarity and ordinary outside physics. Impact, immediate and lingering. The community splits along the dropped assumption. Drop unitarity. Very few are willing. Drop effective field theory outside. That's a big price where experiments agree with it. Drop no drama. That's the firewall. The argument lights a fuse under every later development. Replica wormholes and entanglement islands show how the page curve can emerge without violating outside physics, but they don't hand a free pass to no drama. If the island means the interior is part of the radiation's entanglement wedge, then for an infaller the interior must be reconstructed from what the outside knows. If that reconstruction is state-dependent and fragile, maybe it holds until someone tries to extract too much from the radiation, and then the seam tears. A micro-story captures the mood. A seminar ends with a single sentence on the board. Pick 2, outside locality. Unitarity, no drama. People linger, staring, each quietly crossing out a different word. The fuse Hawking lit now burns at eye level, and nobody gets out of the room without choosing what to save. Fuzzballs, a horizon made of microstructure. While the AMPS fuse burned, string theorists walked up with a different kind of match. They didn't try to keep the horizon smooth, they replaced it. In the Fuzzball proposal, a black hole isn't an empty interior wrapped by a featureless horizon. It's a quantum star made of strings and brains, swollen to roughly the horizon size. No inside in the classical sense. No silent doorway. Just microstructure all the way out. Here's why that matters. The firewall argument starts by assuming a local vacuum at the horizon so that outgoing modes pair with interior partners. Fuzzballs deny that vacuum from the start. If there's structure at the would-be horizon, there's nothing to pair with behind it. The entanglement that creates the smoothness never forms. You don't have to cut a seam if you never sewed it that way. Action, not slogans. In certain supersymmetric settings where calculations are tractable, string theory can count the exact microstates of a black hole and match the Hawking entropy. Then, rather than a single geometry with a clean horizon, you get an enormous space of horizon-scale configurations, each a different arrangement of strings and brains. The black hole we draw in textbooks is a coarse average. Pick one microstate, and the geometry caps off before any horizon forms. It's like walking down a tunnel that narrows into intricate latticework, instead of opening into a cavern. Stakes for information are immediate. If the horizon is microstructure, infalling matter doesn't disappear behind an idealized boundary. It interacts with the fuzzball surface, transfers its details into those degrees of freedom, and later radiation can, in principle, reflect those details, non-thermal at fine scales, thermal only in a coarse sense. Unitarity survives without needing replica wormholes to salvage the entropy curve. The mechanism sits where the action is, at the edge. A micro-story from this camp. A theorist toggles between two plots, one counting microstates in a protected supersymmetric case, one showing the area law. The numbers line up. They lean back, grin, then frown. Great, but where's the astrophysical black hole? The room goes quiet because that's the challenge. Most fuzzball constructions live in special corners of string theory with high symmetry and BPS protection. Translating that confidence to the messy, rotating, neutral giants in the sky is work still in progress. Meanwhile, something else was happening in the Fuzzball narrative: leakage without drama at a distance. The proposal doesn't require violent fireworks for distant observers. Hawking-like radiation still emerges, with an almost thermal spectrum but with subtle, state-dependent deviations that carry information. The difference is microscopic and spread across many quanta. To most instruments, it looks like heat. To an ideal decoder with all of it, it's a message. And what about the person who falls? This is where Fuzzballs and Firewalls part company. Firewalls say the infaller hits high-energy quanta at the horizon because entanglement got cut. Fuzzballs say the infaller meets structure because there was never a vacuum there. The energy scale of that encounter depends on the microstate and the infaller's probe. Some advocates argue that for coarse, low-energy probes, certain correlators reproduce Fuzzball complementarity, a kind of effective smoothness over short times and distances, enough to mimic no drama for a while. But for fine-grained questions, the structure shows through. It isn't free fall forever. It's a soft landing on a quantum mattress that eventually pushes back. Critics push on two fronts. First, can Fuzzballs reproduce the astrophysical signals we actually measure, ringtones, shadows, accretion disk spectra, without obvious deviations? If the surface sits where the horizon would be, echoes or reflections might appear in gravitational waves. So far, searches haven't found robust, widely accepted echo signatures tied to horizon-scale surfaces. Second, even if the microstates exist in protected models, do generic, non-supersymmetric black holes share the same horizonless cap? This is an open door, not a settled hallway. Impact on the big argument is clear. Fuzzballs drop no drama in the strict sense at the horizon, but keep outside effective field theory intact and save unitarity with a tangible mechanism. They don't need an island prescription to lower entropy. The degrees of freedom at the edge write the page curve by hand. If they're right, the firewall isn't a sudden wall of energy. It's the permanent fact that the horizon was never empty. The boundary always talked because the boundary was the system. There's a human beat here. A young researcher stares at a sketch of a capped-off throat and whispers, "So the inside is a myth." Their advisor shrugs. A useful myth until you ask too much of it. The promise of Fuzzballs is blunt. Make the microstates concrete and you don't need paradox to keep score. But to carry that promise from chalkboard worlds to the black holes we photograph, the microstructure has to survive reality's test. That's the next fight.